Hi everyone, so welcome to the 12th lecture of EEE 135 about guided waves. So in the previous meetings, we have talked about plane waves and how they propagate in free space, so-called unguided waves. So in this meeting, we'll talk about guided waves and tie up this concept of a guided wave to our first lecture, which is the transmission line. Okay? So, well, it's actually just transmission lines. When you guide your electromagnetic wave, you're propagating energy through a transmission line. You're actually guiding these waves to travel from one point to the other. And you ensure that the power that you're transmitting is reaching whatever you want it to go into, right? So, for example, if you connect a voltage source to a resistor, the two conductors that you are using to transmit energy from the voltage source towards a resistor, for example, you're using the conductors as a guide for your energy to flow from your voltage source to your resistor. Okay, so recall the concept of transverse electromagnetic waves. So in a TEM mode of propagation, your electric field and magnetic field are orthogonal to each other. Okay, so there are no longitudinal fields. What are that? So longitudinal fields are just telling us that if your direction of propagation is, let's say, towards the z-axis, your electric field or magnetic field is has a component rather that is aligned with the direction of propagation, so called the longitudinal electric field, for example. And this is your transverse electric field. Okay, so for a transverse electromagnetic wave, both the the electric field intensity and the magnetic field intensity don't have any longitudinal component on their while the wave propagates. Okay, so this is possible in a two-conductor line. If we're talking about a guided wave, so for a guided wave propagation, this is only possible if you have at least two conductors in your system. That's why when we're connecting a voltage source to a resistor and we want to guide the power from the voltage from, for example, a battery to a resistor, we need two conductors. So we are able to guide the wave towards that resistor. So any two conductor system can guide your EM wave to a certain direction in a TEM mode of propagation. Okay? So let's put some examples there, some common wave guides, as we call it. So generally, a two-conductor system, or even just a single conductor system, is called a waveguide. So it guides the wave to transfer power. So a parallel plate waveguide uses two planar conductors spaced with a distance h and some with W, such that your fields are traveling towards this direction, okay, or in this direction. That is, okay, there you go. So in this direction or in that direction, all right. So right, I apologize for that. There's a little bit of mishap. So let's repeat that. Okay, so it's either in this direction, okay, going perpendicular to the dielectric right here. So it goes along that dielectric plate. So your electric field will exist between your plates that is patterned like this. So it's in the vertical direction, and your magnetic field is patterned like this. So inside your uh, parallel plate waveguide. Okay, excuse me. So if you have noticed, if you have a sheet current that is in this direction, those three, you're you're producing a magnetic field that is in this direction within your dielectric spacing. And if that is the direction of your magnetic field, okay, then your electric field also has some direction that is uh, aligned with this. So it looks something like this, going down. Okay? And if you get the pointing vector of this system, you will see that the pointing vector is aligned with the direction of the current. So they're actually, when you think of the notion that current transfers power from one point to the other, it's actually the pointing vector that transfers power. So the current is just one way to propagate that power. But the real power that is being transferred, it's not the current, it's actually the electromagnetic wave, which is defined by a pointing vector. So this applies even in a DC system, for example, right? So okay, so we will use the curl equations of Maxwell to determine the electric field and magnetic field within this dielectric. So there's already a time changing electric field and magnetic field inside, and they are coupled because of Maxwell's curl equations. So to derive the behavior of those two, so we will start with this formulation, the curl equation, sorry. So if you expand the curl of your electric field and your magnetic field, you get these equations on the left hand side. And on the right hand side is you just expand it in the Cartesian coordinates. So we're using the Cartesian coordinates because the symmetry of the system can afford us that assumption, all right? So it's easier to work with Cartesian coordinates. So enforcing the symmetry of the system, if you use the boundary conditions, you'll notice that the tangential component of the electric field, so let's go back to the image, the tangential component of the electric field is 0. What are the tangential components? If this is, excuse me, if this is going towards the z-axis, and this is your x-axis, then your y-axis is, I think, would be right here. Okay, your y-axis right here. Your electric field will only exist normal to the planes. Okay, if you enforce the boundary conditions for for a static electric field, you'll notice that the tangential components of your electric field disappears because of the property of your conductor. All right. So with that, the electric field will only exist in the x direction. Okay, so you enforce that, then a lot of these terms will disappear actually. So Ez and Ey will disappear. Okay, so Ey disappears, Ez disappears, and with that, by a consequence, Hx will be 0 because the x component is 0. So Hy will be related to a change with respect to z, and Hz will be related to a change with respect to y. Okay, excuse me. So you get two equations from the curl of Maxwell, from the curl of the electric field rather. For the curl of the magnetic field, we already know that Hx is 0. So this becomes 0, then this becomes 0 also, and also Ey and Ez are 0, then this and this wouldn't matter anymore. And what will only matter is this equation, the x component, and then you get the third equation right here. So this is the simplified Maxwell's equations for a parallel plate waveguide, right? So you further simplify that without loss of generality. You can assume that z is the axis of propagation. Okay. In general, if you have a parallel plate waveguide, in general it can go in any direction as long as it is perpendicular to your electric field. Okay, you can go in any direction. You can go in this direction as long as there is no electric field component that is that is tangential to the conducting plates. All right. Okay. So without loss of generality, let's say that the z-axis is the axis of propagation. Then our Maxwell's equations will simplify into these two simple equations right here. So a derivative or a gradient, a derivative of your electric field, your x component, a change of it along the z-axis will induce a magnetic field. And as that magnetic field changes also because of the change in electric field, this same magnetic field that changes with respect to the z-axis also induces an electric field. Therefore, you have a propagation. Okay, so but we can actually model it. So this is just a specific point between the conducting plates. Okay, so if you remember the image, so this is just a specific point on that conducting plate. We can solve for a macroscopic behavior by getting the voltage and the current, the total current that passes through your uh, parallel plate waveguide. Okay, so the voltage can be solved by getting the integral, negative integral of E dot dl. This is your voltage equation, or the definition of the voltage from way back lecture 4 or 3, I think, if I remember correctly. Okay, the other one is how we define the current, but it's a little bit of a jump to get from here to there. Sorry, from there to here. Right. So for the current, right here, you have to enforce the boundary conditions. So if going back to the image of your dielectric, right, there you go. So the current is related, so at least the sheet current density is related to the magnetic field that is passing through on that plane. So if you look at this plane, so you have a tangential magnetic field. You have no magnetic field outside. So you're assuming that it's only contained between your two conductors. So this is your current, and it has a return path on the other side. Okay, so by the boundary conditions, you get the relation that K, the current, is equal to your magnetic field. So the current density is equal to your magnetic field. So just multiply this with the width of your parallel plate waveguide, and you get the total current. Okay? So given that, we can substitute these expressions. Sorry, yeah. We can substitute these expressions if we express Hy and Ex in terms of the voltage and the current. We can substitute them to these expressions. And we get these two relations, uh, two equations rather, relating your voltage and your current. And this is a callback to your to the first lecture that we had. This is the telegrapher's equation from your transmission line theory. So if you scale up Maxwell's equations in a guided medium, so if you scale it up into that volume of that guided medium, your electromagnetic wave propagation just simplifies into your telegrapher's equations, which is based on circuit theory. So you know that they're related to each other. The voltage wave that you see, or that you observed from way back in lecture 1, that propagates along the transmission line is actually your electric field. And the current that is passing through that transmission line is related to your magnetic field. Okay, and they induce each other and let them propagate with each other. So noting that C is equal to epsilon W over H. So this excuse me, this term becomes J omega C V. And noting that L is mu H over W, then this becomes negative J omega mu Li. Sorry, J omega Li. There you go. You get your telegrapher's equation. And from way back when, during lecture 1, the first lecture that we had, this is the general form of your telegrapher's equation. We can now relate this characteristic impedance with the intrinsic impedance. So if you substitute this, the formula for characteristic impedance with your LNC, get this expression, and then it's related to your characteristic impedance. So this square root of mu over epsilon is the intrinsic impedance of the dielectric, excuse me, of the dielectric between your plates. Right? And beta is still the same. It's equal to omega square root of LC. And if you simplify that, it just becomes omega square root of mu epsilon. So that's for your parallel plate waveguide. Alright. Okay. So next is for the coaxial waveguide. The coaxial waveguide, or the coaxial cable, is two coaxial cylinders with radius A and B respectively, have a dielectric spacing between them. So there are two conductors here, the smaller inner conductor and the outer larger conductor. You can still apply Maxwell's equations similarly to this system, but in this case, you're going to use cylindrical symmetry, so you have to use the cylindrical coordinate version of the curl equations, and they simplify to 6 different equations for your ARO component, AV component, and your AZ component. So these are the 6 equations that came from Maxwell's curl equations. So we can make some more simplifications here. So we enforce the symmetry of the system from the boundary conditions. Again, there are no tangential components for your electric field. There are no tangential components. That means only ERO is the only one that exists. Okay? So with that, we remove this, remove this, remove this, and where else? Okay, nowhere else. So there's also no Z component enforcing the symmetry. So there's no electric field in the Z axis. So the Z component also disappears like this. Excuse me. So is that right? So EZ, yep, there is no Z component. So Z component is cancelled here. Okay, there you go. So we're beginning to simplify it further. So with the TM mode propagation, HZ is also 0. So more simplification yields these equations. Okay? Sorry, not ERO. ERO won't cancel. I apologize. It's EPhi that will cancel. Right. Okay, there you go. Okay, so I apologize for that. EPhi is the one that cancels. So ERO should still exist because that's what the symmetry enforces us. Right. So now we're left with these 4 equations right here. It's a more difficult setup compared to your parallel plate waveguide, but let's try to solve it. Right. So the 4th equation, this one, suggests that rho times hv is equal to some constant, some function that is constant with respect to phi and z, because the partial derivative of this with respect to rho is equal to 0. Therefore, it should be constant with respect to rho, which means that it is a function of only phi and z. So it's constant with respect to rho, alright? That's why we can say that rho multiplied to hv is a function of phi and z. So this is what happened here. So noting that, if we substitute that on the second equation, third equation rather. So if we substitute that on the third equation, so you put it here, then we get this expression for the derivative of hv with respect to z. It's a function of phi and z divided by rho. So this is actually the partial derivative of g with respect to z. Let's just call it f. So it's actually 1 over rho d partial of g with respect to z. So it's equal to f some f phi of z divided by rho. So now that is related to E rho right here. Okay. But because of the second equation, E rho should not have any dependence on phi. So we can't say that E rho is a function of phi and z divided by rho. So we can't say that. So because the derivative of E rho with respect to phi is 0. So that means that this function right here should only be dependent on z. So this should only be dependent on z. Therefore, we can say that E rho is hz over rho. And by consequence, h phi is also some function of z only divided by rho. And now we can substitute them from the first to the first and third equations here and here, and you will see that the 1 over rho cancels out with each other, and then you'll be left with these 2 equations right here. So it's now a differential equation system only with the arbitrary functions h and g that we defined earlier. Excuse me. Alright, so given that, we can solve this system. Okay, but we won't go there yet. We want to learn about the macroscopic behavior of the wave inside a coaxial waveguide. So we have to define it in terms of the voltages and the currents. So the voltage and the current. So for the voltage, you have to integrate E dot dl. Okay, so you're integrating from your inner radius to your outer radius. So you will get this expression for your voltage. For the current, so you have to jump again to a boundary condition, or if you can actually use Ampere's law in this case. So by using Ampere's law, so you enclose the current in a loop, which loop of 2 pi rho. It captures uh, uh, the closed loop integral of h dot dl becomes this expression. So this is h, sorry, not, you don't include the rho. So this is h, and this is your dl. So the closed loop integral of h dot dl is you integrate from 0 to 2 pi. You will see that the rho component cancels out. And then you'll be left with this expression for the current. You can now substitute g of z as equal to current I divided by 2 pi. And your voltage is equal to, or your h of z rather, is voltage divided by the natural logarithm of b over a. Is equal to h of z. So you can now put that back into these equations, and then you'll be left with this, which is still the telegrapher's equation, but for a coaxial waveguide. So for a coaxial waveguide, we let L, we let L be equal to mu over 2 pi ln b over a, and C is equal to 2 pi epsilon over ln b over a. So given that, we can now get your relationship between your characteristic impedance and your intrinsic impedance of your dielectric. So that's how you relate the behavior of a coaxial waveguide or a coaxial transmission line to its wave behavior inside a small point in that system. Okay, so uh, that is the end of the first part of this lecture. So if you have any questions, do not hesitate to leave a comment in the comment section below. Okay, see you next meeting.